Okay. All right, and off we go. So, so new topic for today. So 2.6, we're talking about something called directional derivatives. I want to start off by reminding you of some things that we know. Some things that we know about partial derivatives. And now this is just a repeat of stuff we've already talked about. So let me be kind of quick with this. Partial derivatives. It's the slope of the graph. If you're moving in the appropriate direction, of course. It's a multiplicative factor, right? Now, again, suitably interpreted. If you're going in, that particular direction, input changes, output changes, and all that. Now, here's one I have not written down before, but I claim this is just a way of kind of formalizing, in fact, just the way I defined partial derivatives. If you look at what's on the inside here, this is a nice exercise to work out. What's on the inside there in blue is just a fancy way of saying I want most of the input coordinates to remain constant. Most of these input coordinates are remaining constant because EI is full of a bunch of zeros. Right? And then only one of those input variables is actually changing. There's a 1 in the ith position on the standard basis vector. So the ith input to F is changing. All the rest are staying constant. This is basically what our definition of partial derivative was, just written as a formula instead of as an algorithm. So again, details, good exercise to think through. And then lastly, an innocent observation, very easy to confirm. If you take the formula for gradient, you dot it with a standard basis vector, again, mostly zeros. What you're going to get is the corresponding coordinate of the gradient, namely the corresponding partial derivative. Okay, so all of these things are different takes, you might say, on partial derivatives. Here's another way to say this. These are different takes on what happens if you're moving in the direction of a particular standard basis vector. Notice the prominence of the standard basis vector in all of these takes. And so I'm going to now ask a question, rhetorical question, which is, all right, forget about the fact that I called these things partial derivatives. All of these things are equal to the partial derivative. That means all these things in green are equal to each other. Is that only the case when I'm moving in the direction of a standard basis vector? Or maybe all of these things are equal to each other for any unit vector, perhaps. Seems like a lot to ask. I mean, after all, most of what we concluded here we got out of the fact that we know how to compute partial derivatives, which we do by way of looking at coordinates. Okay. So first observation I want to make, coordinates are overrated. Thinking of a multivariable function as being a function of, as it says in the name, several variables is really kind of an overrated point of view, in my opinion. I think it's best to think of multivariable functions as being things that you don't put in a bunch of variables, you put in a point, which I guess you could think of as having a bunch of coordinates and it made up of a bunch of variables. But let's not think of it that way. Think of it as a point is what goes in and then something comes out. And it's better to think of it as in terms of points and vectors and not in terms of coordinates. Now let me come up here to this extra picture that I've drawn, and eventually, I'm not sure when, I will copy this into the notes in a way that I can share with y'all. Anyway, y'all can screen capture it off of the video at this point, so maybe that's the easiest way for y'all to get this. What's going on here? You see we have two different, this is actually the same picture, repeated twice. The same background. You can see it's a bunch of kind of contour lines, if you will. And, level sets of some function f. And let's start with the picture on the left. Looking at the picture on the left, you see I have an x-axis and a y-axis. And so v, what I've called v here, is a standard basis vector because it's a unit vector. I didn't write that down, but it's supposed to be a unit vector, and it's pointing in the direction of one of the coordinate axes. Right? And that's the rule. When you're talking about a partial derivative, It's got to be in the direction of a standard basis vector, and that's got to be in the direction of a coordinate axis. U is not in the direction of a coordinate axis. So there's this temptation to say there's something more fundamentally natural about V. Because it's in the direction of a coordinate axis. U is not. Well, okay. Here's same picture, same V, same U. And notice I drew my axes differently. Now U is in the direction of a coordinate axis. Now U is a standard basis vector and is therefore a good, simple vector about which good things happen. I already know good things happen. And V is like, oh, I don't know what that is. That's some other unit vector. It's pointing in some weird direction. Right? So this is a silly distinction. How you set up your axes is pretty arbitrary. If you go out into the woods, yeah, they don't have axes set up out there. Right? It's just a bunch of trees. Right? So how you set up your axes in most cases is totally arbitrary. And it's tempting, again, once you have your axes set up, it's tempting to sort of hunker down and say, okay, this is how it is. And so V is a good vector and U is a bad vector. But it's not. That's just arbitrary, meaningless, coincidentally based on how you set things up. Set it up differently, all of a sudden U is a good vector. V is a bad vector. So my punchline here, the reason I brought all this up, any unit vector could have been a standard basis vector if you had just set up your axes the right way. Right? So any unit vector could have been representative of a partial derivative. And so for any unit vector, these things are all equal to each other. That's the big idea there. Right? Basically, all unit vectors, again, are standard basis vectors if you take the right point of view. Okay, so with all of this in mind, I'm going to acknowledge that, okay, we do have to actually sometimes do business with axes set up a different way. And yeah, the way we define partial derivative, okay, to be fair, yes, is based on coordinates. And so we're going to have to limit our use of the term partial derivative to literally standard basis vectors. But the fact that these things are all equal to, wrong color. The fact that these things are all equal to each other is completely independent of how I've set things up and how I've set up my axes. And if I just think of functions in terms of input points, not coordinates, right? And think about the fact that I can set up my axes however I want, all four of these things should all be equal to each other for any unit vector. And with that in mind, here's our definition. Any unit vector, whatever your unit vector might be, does have to be a unit vector. That's important. Unit vector. But this thing here and that thing there and slope of the graph and multiplicative factor, yeah, these are all equal. Again, it's got to be a unit vector that you define which direction and the thing that you dot with, et cetera, et cetera. It's got to be a unit vector. But these four things are all equal to each other. And that's a cool fact, right? The fact that for any unit vector, all four of these things are always equal to each other. Wow, that's very cool. Things that are cool deserve a name and a notation. And, question?
I'm having a hard time understanding. The unit vector is in terms of a standard basis vector?
Oh, I'm saying the unit, whatever your unit vector you may have, there's a temptation to, when someone says vector, for you to think list of coordinates. And this is what I'm trying to pull you away from. Vectors make sense without coordinates, right? So, for example, if I point like this, what are the coordinates of the vector that my arm represents here? Well, I don't know. I don't have any axes set up. It's a direction, right? And there's a magnitude. I've got a direction and a magnitude. That's a vector. But there's no coordinates because coordinates aren't what define a vector. Does that make sense?
So what you're saying is if we adjust where we define the coordinate planes, we can make a unit vector in terms of the vector we already know.
Yeah. Whatever unit vector you take, right? I don't care, any unit vector. What I'm saying is you can choose your coordinate axes with that in mind, right? Let that be the direction of your first coordinate axis, for example, right? And then set up your other coordinate axes however you like, as long as they're orthonormal. And then, now your unit vector is a standard basis vector, and you can talk about partial derivatives, and all of this is old news at that point, and it just comes along for free just because you chose to set up your axes in a convenient way. Okay, so, sure. So these things are all equal. That's cool. Stuff that's cool deserves a name and a notation. The name is directional derivative, and the notation is this right here. Okay, and notice in particular the unit vector that describes which direction we're going as we think about all these things. That unit vector goes there. Okay, yeah.
Yeah, so this is just basically almost the same thing we did when we were doing the derivative matrix, but now we are making it with respect to...
Kinda, yeah. It's very closely related. Yeah, this directional derivative says, hey, I'm at this point A and I'm moving with some velocity, and I want to know how F is changing. You're absolutely right. We previously thought of that as derivative matrix times velocity vector. Here, I'm thinking of it with, I don't want to assume anything about differentiability. I don't even have to. Notice nothing here says that the F has to be differentiable. It doesn't have to be. And this is also just a little bit more sort of immediate. Derivative matrices are kind of sophisticated. This is something I could just kind of write down, literally by way of a single variable derivative. Yeah.
So it's just like
Single variable derivative, yeah. It's less sophisticated. Yeah, right. Okay, now there is one extra thing that you get when you do this. Oh, and let's see, I need to hit that button. There we go. Okay, so one extra thing that we get. Let's think about this multiplicative factor point of view. This, what do I multiply? And notice here I've got, it's what I'm multiplying by input changes, which I think of as either discrete changes ds or rates of change ds dt. To get, let's see, the output change corresponding, and that either df or df dt. And now I ask rhetorically, what do you think we should call the thing that we multiply by ds to get df? And a pretty reasonable choice is to call it df ds. And so just notationally, right, don't worry about it. I'm always telling you can't cancel the differentials. That doesn't make any sense. That's dangerous. Certainly with the chain rule, catastrophic face plant, right? Catastrophes happen if you're using the chain rule. But in this case, it's actually okay. Certainly, it's notationally satisfying, and that's a sufficient motivation to be comfortable with this notation df/ds. And it's a really nice point of view, nice way to think about directional derivatives. In addition to all of what we already had, we already knew that directional derivatives are the slope of the graph. We already knew that it was a multiplicative factor. But now we can think of it as the rate of change of the function with respect to distance traveled in whatever direction you're going. So the rate of change of the function with respect to distance. Now we want to distinguish that from the rate of change with respect to time. Now here's my little analogy. Again, imagine I'm out, and you'd think I hike a lot because I say I have a lot of scenarios where I'm up on the side of the hill. I actually don't hike a lot, but it's a great metaphor, right? And it's some wishful thinking. So imagine that I'm on a trail on the side of the mountain, right? And I'm going up the trail, and the question comes up: how fast is my altitude changing? Okay, well, there's a couple of different things I could have meant by that. One is I could have been asking per unit time, how fast is my altitude change? In other words, what's the rate of change of my altitude with respect to the clock? Am I gaining 50 feet of altitude per minute, or am I gaining 10 feet of altitude per minute? Right? Maybe that's what the question means. That would be df/dt, derivative with respect to time. And the thing about df/dt is it depends on how fast you're hiking. I could conceivably run up the hill, and the df/dt would be large. Or I could slowly, eventually make my way up the hill, then df/dt would be small. Everybody see what I mean by that? But now here's another totally separate question. What is df/ds? How much altitude gain is there per unit distance that I travel? That's literally just asking how steep is the hill, and it's got nothing to do with me. It doesn't matter if I'm running or if I'm walking or if I'm crawling, right? It's just about the hill. How much gain in altitude per how much horizontal movement. Everybody see the difference? Yeah.
Could you please repeat that?
Yeah, so df/ds says how much does the altitude change per horizontal distance traveled, and that's just, again, it's just a height per base. That's literally just the slope of the trail, right? And the slope of the trail is there before I got there. It's going to be there after I leave. The trail just sits there. It's a permanent feature of the hill. And so df/ds is asking about something intrinsic to the hill, right? df/dt says, how am I doing it, right? And if I run, then df/dt is large. And if I crawl, then df/dt is small. Yeah.
So then grammatically, how would the first one look like?
So what now?
The df/ds. Was it just like this?
Yeah. So df is height, ds is horizontal distance.
Oh, okay.
So it's just the slope of the slope of the trail. Okay. That's right. Is that, you good?
Well, the second one then is kind of like your acceleration. Like how
No.
much-
No. There's no acceleration in this. Which one are you talking about? You talking about
So the second one, yeah, with respect to
df/ds?
Yeah.
No, t.
Yes, dt.
dt. So that just says how many feet of altitude am I gaining per minute? Right? And that depends on how, I don't know, are you driving in a Jeep? And well, you gain a lot of altitude if you're driving in a Jeep, right? Or if I'm crawling on my hands and knees, then I'm not going to be gaining a lot of altitude very fast.
I thought you said it was like the rate of change of the change of velocity.
That's not
Or
what this
change of
says.
altitude.
That's just not what this says, though.
Oh.
This doesn't say rate of change of rate of change. It just says what is the rate of change of f with respect to t. That's all that says. Yeah. Is that cool?
Yeah.
Yeah. Okay. All right. So let me show you all an example. Here is a question. It's a bunch of given particulars, and what's the slope of the graph? It says. What's the slope of the graph? Okay, let me come back into here, and I've got you know what? Let me do this in blue. Keep my colors straight. Slope of the graph. The question says, okay, well, slope of the graph is one of my interpretations of directional derivative. So this question, fairly bluntly, is just asking us to compute directional derivative. Okay, now how are we going to do that? How are we going to compute the directional derivative? Let me clean up the mess. A lot of stuff on here. It's just too much. Overwhelming. If I can't get that thing, there we go. Okay. Slope of the graph is directional derivative. How am I going to compute it? I'm going to compute it with this formula right here, right? I like this formula a lot. The thing I like about this formula is it's the gradient, which is made up out of partials, which are world's easiest derivatives, and then a dot product. Super easy. Nothing to it. Everybody happy? Okay. So, slope of the graph is directional derivative, computed with a dot product with the gradient. That's basically it. There's a couple little details that I need to talk about here. That's the meat of this example. Slope, directional derivative, dot product with the gradient in business. Okay, first little subtlety. You gotta be real careful about this. Directional derivative requires that vector must be a unit vector. That's a big point. It's got to be a unit. If you want to use all these interpretations, and you got to stick to the definition, and you've got to use a unit vector. Were we given a unit vector? Nope. Sadly, no. So that's not acceptable, right? I can't just say directional derivative as we have things defined. I cannot say directional derivative and use 3, 4 as my direction vector. Okay, but notice the question actually said the direction of that vector. The direction that vector 3, 4 points, yeah, I can totally write that down. The direction it points is what I get when I take my non-unit vector and divide it by its own magnitude. That is now a unit vector. It's a unit vector, and it points in exactly the direction of the vector that I was supposed to use to define my direction. So that could be my U, goes there, and we're in business. Is everybody happy? All right. The other thing I want to point out here, just another little sticky wicket and a little landmine you can step on. It's real easy to mess this up. It's about the phrasing. Y'all remember, we've talked about vectors and points, and we use the same notations because for any point there's a vector, any vector there's a point. They're canonically isomorphic, right? They're kind of, it's not exactly they're the same thing, but if you conflate them, no problem. You can always determine which one was meant from the context, from the statement of the question of what are you doing with this thing. Now, the first giveaway that this is to be understood to be a vector is that I explicitly wrote it. That's a pretty blunt giveaway. That's a vector, not a point, right? But the other giveaway, and this is sometimes going to be the case, sometimes that won't be written. It says right here, the direction of that vector. Points don't have directions. Right? Vectors have direction and magnitude. Points have location. So this says direction, that means this is a vector, that means this is not a point. So here's what, unfortunately, some students sloppy on this issue will do, and this is tragic. Students will say, okay, well, apparently I'm at the point 3, 1. Okay, there's 3, 1, I guess. We're calling that A. Fine. And then they'll say, 3, 4. I see 3, 4. And then they draw 3, 4 as a point, and then they mistakenly interpret in the direction of as meaning toward, which is not what that means, but it's kind of sloppily, carelessly, kind of feels maybe like that's what that means. And so if you mistakenly interpret that as toward the point 3, 4, then you would end up going that direction, which is the wrong direction. Does everybody see how that's the wrong? Okay, yes.
Could we also just look at the fact that the V has a hat or
Well, no, I hear what you're saying. The little arrow sort of hat thing, yeah. Not really, because we use that to represent points as well. So remember, we use in notation, we kind of conflate the distinction between points and vectors. This is very common because again, the context will always be your guide as to what should I interpret it as a vector or should I interpret it as a point. So you can't use the notation on that. Now, some books, ours included, at least most of the time, use separate notations, and that has its own problems. And so I have always been on the school of thought of, interpret appropriately to the context, and then we get to share all the same convenient notations.
So toward is for a point, direction is for a vector.
Yeah. The word direction is part of the definition of what is a vector. Yeah. Right. Okay, last one. We got to move. Yeah.
weren't given we weren't told the direction of the vector, and we just given 2 points, would you just get the?
Yeah. If I were to give you a point and then say move toward a certain other point, then you'd subtract, and that would be your vector.
Okay.
Yeah. Right. Okay. All right. Another example, and this one's very, very analogous. It is a little bit different. This says certain particulars having been given. What is DTDS? Okay, well, what is DTDS? Let's go back to up here. Excuse me. I want to compute DTDS. Derivative with respect to distance is one of my interpretations of directional derivative. So again, the question has asked me to compute something that ultimately is a directional derivative, and so okay, I'll compute it with, again, that same formula. Right? This is keying that's just off of a different interpretation of directional derivative. So again, same start. What I was asked is a directional derivative. I compute with this formula. We've got this same little unit vector issue where this vector is not a unit vector, but the direction that it points is that unit vector that you get by dividing the dividing the original vector by its own magnitude. Same little curveball. Okay. And again, basically the same deals. You compute the gradient, you plug in the given point, you do the dot product. Very, very similar. Everybody good? Somebody asked in one of my earlier lectures, so basically in this example, you're computing effectively also the slope of the graph. And kind of, sort of, but very, this is an awkward take, I'm going to say, because look at this function that we're talking about. This function has 3 input variables and 1 output variable. If I wanted to make some interpretation of this in the context of graphs, that graph's a 4-dimensional picture. And weird, right? I don't know how to interpret. That's introducing a level of confusion that's not particularly beneficial. Okay, so I just wanted to point that out. Okay, yeah.
So there's no way to visualize this?
There's no way to visualize it with graphs. But there's plenty of ways to visualize functions of 3 variables, like level sets are a pretty good choice. Yeah, so again, this is why, right, I'm trying to pull everybody away from this reliance on graphs. So I get you. I know where you're coming from. But we want to avoid that way of thinking. Yeah. Okay, bad news. I'm sorry. It's not my fault. But we have a cultural issue here that creates some confusion. There are those who will remove the requirement that it be a unit vector. Now let's go back and think about what that will do to us. How does that change things? And now I need to erase here. And let me, oh gosh. Okay, so let's do it about like that. Okay, there we go. So so as it stands, and by the way, let me be clear. In Math219, we're doing this. This is how the book defines it. This is what we're doing in Math219. I don't want there to be any ambiguity on that. Math219 is a unit vector directional derivative context. All right? So perfectly clear about that. So with this assumption that we're talking about unit vectors, the directional derivative, that notation, defined by that formula, computed by that easy formula, interpreted as a slope or a factor or a rate of change with respect to distance. Cool, directional derivatives. All right, now, when these other people come around and say that they're going to remove the unit vector requirement, everything changes. Well, correction, some of this changes. When you remove that unit vector requirement, you no longer can interpret this thing as being slope of a graph. It's just not. It doesn't work out. Changes. Everything changes. It's no longer a multiplicative factor, and it is no longer DFDS. And that makes it seem like this is a bad idea. Why would we remove a requirement that results in us losing interpretations? And the answer is because when you remove a requirement, this now applies more broadly. I can talk now, if we take this modified definition, now I can talk about directional derivative for any vector. And here's the thing. This notation, fine. This formula, fine. Representing how fast the function is changing with respect to time. Natural. That's something we want to know sometimes. Sometimes you want to know, I don't care about distance. Sometimes you want to know, in fact, as I move, how fast is this function changing with respect to time? Perfectly reasonable thing to want to talk about. This does it. This formula computes that. This is a really useful idea that applies very broadly. And that's a good thing. Right, so anyway, bad news, good news. Bad news is there are different people make different assumptions about what the word directional derivative means. It's crazy, but that's just the reality that's the state of affairs. So, again, not my fault. That's the way it is. I just got here, right? But I want you all to be aware of this. So when you are outside of Math219 and you're talking to Professor so-and-so in the engineering school and he says directional derivative, you're going to need to look for context clues. Wait a minute. Is he one of these is he a unit vector subscriber like Kali is and like Math219 was? Or is he one of these non-unit people who changes the definition to get a broader thing that has less, but still valuable interpretations? And you don't know, right? So you got to be careful about that. Make sure to figure that out. Don't just assume. Also be aware that other people, like if you say directional derivative, be aware that other people might misinterpret you, right? And so you got to be careful about that, yeah.
So because we're not using a unit vector, the result is, what's the difference?
The difference is that some of these interpretations just don't work anymore. Yeah, so you get to apply this more broadly to any vector, but you do not get to say it's df/ds. It's not the slope of the graph. It's not a multiplicative factor as we've described it here.
So what is it?
It represents how fast the function's changing with respect to time. Okay. Yeah, which again is a very natural thing to want to talk about, and it is still computed by this handy little formula. That's all good. Yeah. So, okay, heads up, be aware. By the way, just in case you might be curious, again, I cannot emphasize enough, in Math219, in Math219, we are sticking with this one because Kali does, right? Our book does it this way, so this is the way we're doing it. But just so you know, outside of Math219, I removed that unit vector distinction myself. I'm one of those people. So this is full disclosure, right? It's a pro-con thing, right? And there are situations where I revert to this, but there are some really nice advantages to that other point of view. Okay, all right, enough of that. Okay, let's talk about this question. This is what I'm going to call a natural question that has a really interesting answer. I'm just going to approach this as a question for no particular reason. We have a nice function f. We're sitting here at a certain point A. And let's see here. We are entertaining the question of all possible directions that I could move from A. And I'm eventually going to pick one, but I haven't picked one yet. So a bunch of different directions that I could move, right? I'm standing, and I'm like, I could go that way, or I could go that way, or I could go, which way should I go? Right? Thinking about my options. And in particular, what's going to decide that for me is that I'm interested in looking at the directional derivative. There's some function here, f, and I want to know how fast that function's changing. And if I go off and move in some direction, the function will be changing at some rate. But if I go in a different direction, the function will be changing at a different rate, right? This directional derivative depends on which v vector you pick, because again, that is part of what a directional derivative is. So the reasonable question we want to ask is, all right, which one of these unit vectors maximizes the directional derivative? Which one makes f increase as fast as possible? And do keep in mind we're talking about unit vectors, right? So there's a temptation to say, okay, well, if I want f to be, increasing as fast as possible, then pick a direction and run really, really fast in that direction, right? But no fair, no, unit vectors only. We want to distinguish directions. We want to kind of factor out magnitudes out of the question. Okay, does everybody understand what the question's asking? Okay, now let's talk about language before we actually answer the question. This direction that maximizes the directional derivative. There's two terms I want to introduce y'all to. The one that I think makes the most sense, and this is just me, but I think direction of fastest increase. I think it makes loads of sense. Directional derivative says how fast is f increasing. I'm looking for the direction that makes how fast it's increasing as big as possible. I think direction of fastest increase just gets right on that, right? That's explicitly exactly what we're trying to do. Right? Reasonable? All right, here's a different point of view. A lot of people like to call this direction of steepest ascent. Let me explain why. If the function that you're looking at, that you're trying to make increase as fast as possible, if that direction represents height, let me just keep out of that. If it represents height, in other words, if you're looking at a graph of f, when you're looking at a graph of f, typically the value of the function is height, right? Well, then increasing the function as fast as possible, if the function is height, means you're increasing your altitude as fast as possible, means you're moving in the direction that has you climbing the mountain as steeply as possible. You can see the motivation for this term, steepest ascent. So that's a point of view, yeah.
Could you repeat that for the
The what now?
the first one?
Oh yeah, well yeah. So the idea here, if the directional derivative, that's the thing you're trying to make as big as possible. If that's representing how fast the function's increasing, right? Then fastest increase, because we're making the rate that it's increasing as large as possible.
Rate of the function, right?
The what now?
The function.
Yeah, f. Yeah, right. Yeah, exactly. Okay. So yeah.
Sorry, fastest increase, but we're not taking it with respect to time.
Correct, because we're not interested in magnitudes, we're not interested in speeds, we're interested just in directions, right? And so yeah, we want to get time out of the problem. Like if you want to decide, what's the fastest way from here to back to your dorm room or whatever, and you're like, well, we could go around the forest or we could go through the forest, which is better. Well, if you have two friends that are going to do it and see who gets there first, and if one of them's on the track team and the other one is, me, right? Right? Then that's not fair, because the person on the track team is going to get there faster than nobody. We don't want speed to enter into the comparison, right? We want to just compare just the directions. So we're thinking of all these as being, again, directional derivatives, which are derivatives with respect to distance, not time. All right. Okay, so just so you know, and I think this is unfortunate, but oh well, that's the world we live in. While I like this term the most, this is the term that's actually the most common, steepest ascent. And I think that's weird, because it only makes sense if you're looking at graphs. Very often we're not looking at graphs. Very often we don't want to look at graphs. Very often we cannot look at graphs. Sometimes graphs are four-dimensional. This only makes sense in a context that may not be relevant to us, fastest increase always makes sense. So I'm going to mostly use fastest increase. Be aware, outside of this class, you're going to hear steepest descent a lot. Okay, so how do we answer this question? This is pretty straightforward. Again, directional derivative is what we want to maximize. Let me just compute the directional derivative. It's this dot product. Dot products are these expressions right here. Don't forget our vectors are unit vectors, so that magnitude is 1, so let's lose that. This is what we're actually trying to maximize, arguably, and in fact, I can simplify that too, because keep in mind, I'm at the point A. I haven't moved yet. I haven't even decided yet which direction I'm going to move. That point is fixed. A is a constant, and therefore the gradient at that point, it's going to be some formula, but it's evaluated at a point that's not moving. So that gradient is also a constant. So this is a constant. So altogether then, I want to make this as big as possible. I just need to figure out how do I make cosine theta as big as possible, and that's an easy one, right? That's a flashback to trig class. Cosine theta is as big as possible when it's 1, which happens when theta is equal to 0. And so keeping in mind then that this is theta, theta equals 0 would mean that my v vector, right, that I had drawn that way, well, now I need that angle to be 0. That means I need my vector v to point in the same direction as the gradient. So that's the lovely little answer. You want to find the direction of fastest increase? Cool, go in the direction of the gradient. Nice, pithy, crisp little answer. Yep?
Is that generalizable to all problems like this, or just this one?
Yeah. The direction of fastest increase is always the direction of the gradient vector. Yep. Nice and simple. Next natural question is okay, cool. So that's the direction that makes directional derivative as big as possible. All right. How big is it? That's the biggest it can get. How big is that? And so you compute, keeping in mind that our velocity vector here, our direction vector, is the direction of the gradient, so gradient divided by magnitude. And then you notice that we have a self-dot product, which is a magnitude squared. And punchline, the magnitude of the gradient. So what's really wild about this little study we've done, we asked, hey, what's the right direction to go? And how fast is the function increasing in that direction? And in both of those questions, the answer is the gradient. The direction of the gradient, the magnitude of the gradient. It's the gradient. So this gives what I think is a really nice point of view on this little exercise, and that is what I call a geometric characterization of the gradient. Reminder, previously to now, before today's class, right? Gradient was an algebraic construction. It was a shorthand that allows us to streamline linear approximations. It was just a notational convenience. That's it. Right? Now it's a geometrically natural thing. The direction is natural. The magnitude is natural. The direction is the direction of fastest increase. It's a natural thing. The magnitude is a natural thing. It's the rate of change with respect to distance. It's the slope in that maximal direction. If you're thinking about a graph. So how steep is the hill? Magnitude of the gradient. Everybody good? Okay, yeah.
I have a question. When we're doing the gradients, the times where we have like two different functions and then we arrange the gradients to like a matrix.
I'm sorry, I didn't hear that part of it.
There's a time when we're doing like linear approximations and derivative matrices.
Yep.
There's because in the homework is a point where we had like two functions, and so we arranged the partials into a matrix. So in that case, how would you get the math?
So you were saying if you reinterpret the gradient as a derivative matrix? This sounds like an office hours question. Can we talk after class?
Yeah.
Okay, yeah, that'd be good. Okay. All right. Okay, so let's see an example. Here we go. We've got a hill that is in the shape of the graph. Keep in mind, graph means that height is what the function is, right? So graph z equals. And in this particular scenario, we've got a formula for altitude. And I'm at this point, 1, 3. Right? Okay, well, to be fair, I'm actually I'm at the point sitting above 1, 3, right? Let's not be silly. 1, 3 is in the domain. I'm on the side of the hill. I'm not buried underneath the hill, right? I'm not in a two-dimensional world. I'm up on the hill itself in a three-dimensional world, and that's the first observation I want to make is heads up for this annoying sort of distinction that we have to worry about. When you're looking at graphs, right, there's a distinction between the point on the graph and the point in the domain that gives rise to that point on the graph. They are different things, in fact, right? But even though they're different, I mean, they're kind of, it's not they're exactly the same, but, it's very convenient to talk about your location on the surface of the Earth with just longitude and latitude, just map coordinates. Because if you tell someone where your map coordinates are, they're going to go ahead and assume that you're on the surface of the Earth, right? Of course they are. Unless, I'll say, if you're not on the surface of the Earth, then you should clarify when you send the map coordinates, by the way, I am 500 feet down a mine shaft, okay? Right? So I've gone to the trouble here of explicitly distinguishing the map coordinates from the point on the graph corresponding to those map coordinates, and that will not always be the case. Right? This is something that it's just a little tedious to constantly say I'm at the point sitting above 1, 3. It's so much easier to say I'm at 1, 3, and then you as the listener have to understand that, well, yeah, of course I'm on the graph, and so I'm at 1, 3, whatever z is. Does that make sense to everybody? Okay. All right. So let's see here. We're almost out of time, but we can finish this. This is actually pretty quick at this point. The question says, which way is uphill? What's the direction of steepest ascent, effectively, they're asking. That's just the direction of the gradient vector, so we compute the gradient. And don't forget to plug in. We're at the point 1, 3, and so you compute the gradient at the point 1, 3. It's about like that, and that's the direction of fastest increase, which, by the way, you can see on the picture. If I'm here, that is the direction that I should walk to go uphill.
So that's the same then for both the point on the plane here and the point on the graph?
Well, so gradients are always within the domain. So this is another one of these things that, it's kind of a given, right? If you're on the hill and if somebody says, here, walk southwest, okay, you probably knew that they didn't mean tunnel into the hill, right? They'd mean, walk up the hill, of course, right? But southwest tells you the direction that your map coordinates should move because the gradient's in the domain. Yeah, right. Yeah, sure. So that's another kind of a sloppiness of the language, but it's very standard. And let's see, how steep is the hill? How steep is, well, what is the slope in that direction? What is the value of the directional derivative? That's the magnitude of the gradient. And that's, again, easy calculation. Okay, test on Friday. See you then. Have a good one. Good luck studying. See you soon. And don't forget about attendance.